Hello everyone. Today I will talk about Gibbs Paradox. This is a famous concept or you can say, a famous paradox in thermodynamics, also in statistical mechanics. We'll see the problem and we will try to solve what is going on here. First, we'll know a little bit about entropy, then we'll see the statistical mechanical approach. Also see what is the problem and what is the physical significance of it. Okay, so start from entropy. What is entropy? It is not a measurable quantity like temperature, pressure. We can only measure its change. I mean, the change in entropy we can only measure. Later, a misconception will come, and I will then tell what is exactly happening there. According to Boltzmann, entropy is a measure of disorder in molecular arrangement of a system. Clausius also give a statement that from the second law of thermodynamics, only such process can occur for which entropy does not decrease. He is talking about the entropy globally, not locally. If you can think that you freeze water to ice, then the entropy of the system is decreases. But it decreases locally, not globally. You have to pay some energy. So if you calculate the total entropy of the universe, it's always increasing. Nature supports entropy, evolves towards states of the higher entropy. Entropy has some properties. I will not talk about them like it is path independent, blah blah blah. So now come to the statistical mechanical definition. In statistical mechanics point of view, entropy is basically represent number of microscopic configuration corresponding to a macroscopic state. Okay, so you can read about the entropy in any statistical mechanics book or any thermodynamic standard book. Now we'll start the derivation. So we'll start from the formula. The famous formula is KVLN omega. So here omega is the number of microstate, KV is the Boltzmann constant. Here the little misconception come. How we can calculate entropy? We already told that we can calculate its change. So from the equation we can calculate entropy. So where's the problem? Now in this equation you can see S will be 0 only when omega will be 1. So if the microscopic configuration is 1, then the entropy of the system will be 0. So when it is possible? So if you think logically that it is possible only when the system is freezes like at 0 Kelvin temperature. So at that temperature everything freezes. So this is the only one microscopic configuration that is possible. So we are taking that at 0 Kelvin, absolute 0 temperature, entropy is 0. So actually we are measuring here also the change in entropy, not the absolute entropy. We are taking at t equal to 0, S is 0. That's why we are taking, we are talking that this is the absolute entropy, but this is not actually. Okay, it's fine. Now we are taking a classical gas system and taking classical gas molecules, they are distinguishable. Now for n number of molecules contained within volume V and temperature T, total number of microstates will be the following. Now, I'm not deriving this equation here. You can see it Patria or any statistical mechanics book. This will come from the phase space model. This is very ordinary things. Now, in this equation, you have to do two things. One, you have to put energy is 3 by 2 nkbt and use the famous Stirling approximation. Then you can calculate the entropy. Use that equation S equal to kb ln omega. So you will land at this type of equation. Now, so this is the equation we'll use for the entropy of gas mixing later. Okay, now we'll calculate the entropy of gas mixing. So this is our system where we have one container that is separated by some wall or barrier. In the first portion there is gas 1 and second portion is gas 2. Gas molecule mass of first gas is m1 and the second one is m2, and you are all familiar with the n1, v1, p, t. I am not talking about these variables here. So here we are taking that entropy of gas 1 is S1 and entropy of gas 2 is S2. So before mixing, total entropy S initial is just sum of them, S1 plus S2. So we have, you can see here, we have taken temperature as constant here. So that the system has already, the system can already establish the thermal equilibrium. And we are also taking the pressure constant. You can, I will show you later where this actual pressure, it will help, where it will help us. Okay, I will see you that when it comes. Okay, now we have the equation 2. Now from that we can calculate the initial entropy and also calculate the final entropy. Okay, let's write one by one. So this is the S1 and this is S2. You can calculate it. I am not talking about them because these are the mathematical steps. So this is the entropy before gas mixing. Now we are calculating after gas mixing. So this is our, we are denoting this S1 prime and S2 prime. So entropy after gas mixing will be S final, this is S1 prime plus S2 prime. Now change in entropy we can calculate by just subtract them SF minus SI. So if we calculate the we'll get this type of equation, N1 kV ln V1 plus V2 by V1 plus dot dot dot. So you can see this equation is always greater or equal to 0 because the quantity under log, this is a positive quantity and this is greater than 1 and all quantities are positive here. So delta is obviously greater or equal to 0. And this is also fine and makes sense because when you are mixing two different type of gas, they will mix and it's like a irreversible process. So entropy is increasing here, which is making sense also. Yeah. Now we will take same gas mixing. I mean, before we are taking two different type of gas in two container. Now we'll take same gas in two container and we'll see what is happening here. Now this is our system. So temperature is T, pressure is P, volume V and N. After mixing, temperature and pressure will be same, volume will be double, and the number of particles will be also double. Yeah. So now we are trying to calculate the entropy. So from the above equation you can see this is coming like 2 ln 2, and this is also a positive quantity. That's mean entropy is increasing. Now think logically. We are taking two portions of same gases. We are allowed to mix them and then separate them again. But there is no difference between the initial and the final state of the system. So you can consider it like a reversible process. So here entropy should not change. So logically the entropy should be 0, but mathematically it not come. So where's the problem? So according to Gibbs, the molecules in the case of the same gas has to be indistinguishable. We are taking one example to understand it. Okay. So now think there is a home where 5 brothers are staying in their 5 rooms. 1, 2, 3, 4, 5, and 5 brothers. We are calling them like A, B, C, D, A, B, C, D, E. Okay. So from permutation and combination, we know that they can stay in that room in 5 factorial way. Okay, so you can also do the combination and you can check the combination will become 5 factorial. Okay, but according to Gibbs, we have only the information about the number of the gas molecules. Like think 5 brothers are twins. All are identical. We cannot distinguish them. Now their combination is only 1. So now you think we are all treating them. We are treating them like A. So now you cannot distinguish that E is staying at room 5. B is staying at room 2, or B is staying at room 3. Now you cannot distinguish. So there is only one state. You can consider it like one microstate corresponding to the macrostate. So the home is the macrostate, and they are staying in the room. The configuration is the microstate. Okay. So what's the problem? Actually, by treating the classical gas molecules distinguishable, we are overestimating the number of microstates. That's why the problem comes. Now, so we get the number here 5 factorial, as we are taking 5 brothers. So for n number of molecules, if we divide the microstate with n factorial, then the paradox, I think, that should solve. So we'll come from the do from the beginning, where we use that equation omega this one. So now here we introduce the n factorial. So this is our omega modified. So omega modified is nothing but omega by n factorial. So due to that, S will change, and we are writing the quantity, the new quantities as mod, like modification. So the S will now be written as okay. So let's say this is our system right now. Okay, it has 2 portions, but both gases are same. In the first portion, there is n1 number of molecules, volume is P1, pressure and temperature same. And in second portion, number of molecule is N2 and volume is V2. So S modification, it comes from the general equation, so it's subtract. So that's mean entropy is decreasing little bit. S minus kb ln n factorial. So in our case, it will be written as S1 minus kb ln n1 factorial, because in the first portion there is n1 number of molecules, and following for the second one. Okay, now we are allowing the mixing. Okay, and this is now our initial entropy, initial modified entropy. Okay, so you can see Si is our primary entropy, and this is our modified entropy. So they are differs by some quantity. You can see here. We can similarly calculate the final modified entropy like this way. So you can see that's also differs by some quantity. Now we'll take the change in entropy, modified entropy. Okay, change in modified entropy. So this is basically SF modified minus S initial modified. So putting those values, SF minus SI, this we have already calculated. We will put those values here. So after putting values, these steps comes. Now we'll use the ideal gas equation. Here actually the pressure, the equal pressure, these things is help us. So we'll take the ideal gas equation, PV equal to N kBT. From that we can calculate N by V. So as pressure is constant, that's why we can write P by kBT is constant. So we can write N1 by V1 is N2 by V2, because they are constant. Actually, the right side is constant, so we can write that. So at the beginning we have taken pressure is constant. Pressure is same for both container. So actually it helping us here, so that we can use the ideal gas equation. Okay, so from that we can calculate V1 by V2, that is same as N1 by N2. From that we can calculate these two equations. Now we'll you can see the steps here. There is a term V1 plus V2 by V1 and V1 plus V2 by V2 in the delta S modified equation. So we'll change them by N1 plus N2 by N1 and N1 plus N2 by N2 respectively. Now let's see what's happening. So after putting those values, this is our equation. Now just break the steps and you will get the result 0. So the paradox problem is now solved. So from the we can make a conclusion here that we have to treat the classical gas also. When we are dealing with some gas, we have to treat them as indistinguishable. Indistinguishability of identical particle is one of the fundamental assumptions in quantum mechanics. So from now, when you will treat a gas or gas system, can be classical or quantum, consider them as indistinguishable. Thank you. I think it's clear for all. If you have any problem, you can comment me. I have on Telegram group. You can message me there. Thank you.